The average adult human body runs on roughly 1.5 gallons of circulating blood. Yet, if you track the fluid dynamics over a single day, the kidneys filter the equivalent of this massive 40-gallon yellow column. That means your entire blood supply is forced through the renal system every 45 minutes. To handle that kind of throughput, the kidney operates as a brutal, high-pressure industrial water treatment plant. This continuous turnover is an absolute biological necessity. Without it, normal metabolic waste products would quickly accumulate in the bloodstream and reach lethal toxicity. The mechanical hurdle the kidney has to overcome is scrubbing those microscopic toxins out of a highly pressurized fluid line. The core problem is figuring out how to extract the waste without accidentally purging the pure water, sodium, and glucose that the machine requires to stay alive. The common assumption is that the kidney acts like a smart chemical sponge, actively hunting down and absorbing only the dangerous molecules. Moving at the speed of human blood flow, a highly targeted extraction model is physically impossible. You cannot individually pluck microscopic toxins out of a fast-moving fluid. Instead, the kidney relies on indiscriminate purge. It throws almost everything out of the blood at the exact same time. By flushing out the good with the bad, the body immediately puts its entire fluid supply at massive thermodynamic risk. In a closed hydraulic system, performing an aggressive, indiscriminate purge, followed by meticulous selective reclamation, is the only viable way to ensure the blood gets clean. When you magnify the inner tissue, you find the hardware built for this purge. These dense white pipes are nephrons. Each human kidney contains about 1 million of these continuous industrial units. At the very head of each nephron sits the glomerulus. This is the violent initial extraction point. This diagram details the glomerulus as a knotted ball of highly porous capillaries, handling the incoming blood flow. Blood arrives under immense hydrostatic pressure. That mechanical force violently squeezes fluid out through microscopic holes in the capillary walls. Because it relies purely on size, heavy proteins and red blood cells stay safely inside the vessel. But water, sugars, salts, and toxins are small enough to be pushed completely through the barrier. This newly separated, highly toxic pool of liquid is called the filtrate. Pushing fluid through a high-pressure sieve completely guarantees that the toxins are removed from the blood, but it simultaneously creates an immediate crisis for the body's hydration levels. The flaw of the glomerulus is that its filtration is too effective. If the body actually excreted all of the filtrate it just produced, you would experience severe dehydration and total organ failure within minutes. The blood that survived the glomerulus is now dark, thickened, and desperately needs to be protected from a total fluid collapse. To prevent this, the kidney requires a secondary system engineered with one specific goal: to reverse the massive volume loss. The true mechanical genius of the kidney lies in how it hacks the laws of physics to reclaim the exact amount of water it just threw away. That emergency recovery happens in a specialized structure called the loop of Henle. As shown here, it's a long, stark white U-shaped tube descending deep into the kidney's dark inner tissue. On the way back up, the loop forcefully pumps heavy amounts of salt out of the tube into the deep surrounding tissue. This leverages osmosis, a physical law dictating that water will inevitably be drawn toward areas with higher salt concentrations. The heavy salt gradient acts like a powerful magnet. It passively and magnetically drags pure water right out of the descending side of the tube. Stripped of its water, the filtrate remaining inside the loop becomes drastically darker, thicker, and highly concentrated with waste. By establishing this passive water recovery, the kidney concentrates the lethal toxins without having to spend massive amounts of mechanical energy pumping the water itself. The efficiency of this gradient relies on a fluid dynamic known as the countercurrent multiplier. In this simulation, you can see how fluid flowing down one side of a U-tube and up the other creates a compounding effect, multiplying the saltiness at the very bottom of the loop. This opposing flow is so efficient that the kidney successfully strips 99% of the pure water back out of the waste fluid. The 1% of toxic fluid that survives the entire journey to the end of the tube is what we finally excrete as concentrated urine. A brutal, indiscriminate purge is transformed into a highly precise, survival-ensuring filtration method. When we zoom out from the microscopic nephron to the macro scale of the human torso, the full mechanical cycle comes into view. The reclaimed pure water now sits in the deep tissue of the kidney. entirely separated from the toxic urine. As seen here, this pure water rapidly re-enters the body's vascular system, diluting the thickened blood that survived the initial filtration. Freshly cleaned and fully rehydrated, the blood exits the kidney and surges back toward the heart. This continuous loop repeats relentlessly, securing the chemical balance of the entire blood supply. The kidney operates by blindly throwing almost everything away, only to meticulously steal back exactly what the body needs to function. Controlling exactly how much water and salt is reclaimed versus how much is excreted gives the kidney a distinct mechanical authority. Because blood is primarily composed of water, the volume of water the kidney chooses to retain directly dictates the total volume of blood inside the vascular system. Looking at this cross-section, that blood volume connects directly to hydrostatic pressure. Pumping more volume through the same pipes creates higher pressure against the arterial walls. By dictating exactly how much fluid returns to the system, the kidneys actively manage the hydraulic pressure of the entire human machine. Because they engineer this exact volume of fluid, the kidneys serve as the ultimate regulators of systemic blood pressure.